Hello, we are going to see today chapter 9, flow over immersed bodies. So in last chapter we learned about flow in pipes, that's viscous flow in pipes. That's what we call as internal flow. Now in general I can say there are two kinds of flow. One is internal flow, flow in pipes, and another flow is external flow, is over the body. So flow over immersed bodies has to do with external flow. Our bodies are immersed at this moment in this ocean of air. Let's say you are driving a car. The car is immersed in air, and flow over a car, if you analyze that flow, that's your flow over immersed body. So any body that is immersed in a fluid, whether it is your car, whether it is a submarine, whether it is an airplane, it is immersed in fluid, and then we try to analyze that external flow, and then we understand these forces, lift force and drag force on this flow. That's simply our flow over immersed bodies, and that's what we are going to learn in this chapter. So here we have a car, or this is a simulation of an F1 car. So in this chapter we consider various aspects of flow over bodies that are immersed in a fluid, whether it is aeroplane or automobile or submarine. These are the bodies, these are the flows that we are going to analyze over the body. The object is completely surrounded by fluid, and the flows is termed as external flow. So this one is important. So pipe flow is internal flow, this one is external flow, and that's what we are going to do in this chapter. We are going to understand that external flow. So in this chapter we are mostly going to learn is something, a lift force and a drag force. So these are the forces every time you are moving with some velocity, with relatively higher velocity in the fluid, let's say this bike or a car or a truck. Whenever you move any body through a fluid, there are two kinds of forces, they act on that fluid. One is known as lift force and another is a drag force. And if you want to have an efficient design, you need to understand these forces. So if you want to design an efficient car, or you should have efficient aerodynamic design, then you need to know these forces acting on a body, and then based on that you can learn more about the design, you can make efficient design. So that's the general idea. So that's what we try to do. We try to understand this lift force and drag force. So to understand these forces, what we do is we fix our coordinate system to the object. So here let's say I have a disc or a bullet or a plane, and then these objects are moving, and the fluid around it, let's say air in this case, is relatively stationary. It's not moving, but what we assume is that our coordinate system is fixed. So we fix our coordinate system even though object is moving. We assume that object is fixed and the air stream is going over the object. So that's what we do. We fix our coordinate system, and then we try to analyze the forces, lift force and drag force, forces in x direction and forces in y direction due to this flow. That's what we do here. You can do it in another way. You can put your coordinate system somewhere else and you can still try to understand that. In this case, your object is moving relative to coordinate system, but it's a lot easier to do that. You fix your coordinate system on the object, and then you try to understand these lift forces and drag forces, or forces in x direction and forces in y direction. So what are these lift force and drag force? What exactly it is? So let's say I have an object, let's say this is an aerofoil here. I have an object here, and then there is some fluid stream, let's say air, with some velocity, let's say it's 50 meters per second. Some velocity is going through on this aerofoil, and then this object is completely immersed in the fluid. Let's say this aerofoil is in wind tunnel. In that case, the forces, all the forces which are acting in y direction, in this case what happens is that there is a pressure force acted on the surface of this body in upward direction. That pressure force is normally perpendicular to the direction of the fluid. So direction of the fluid in this direction, so force will be in upward direction, and that's your lift force. So it's going to go upward, and that's your pressure force or lift force. And then there is another force known as drag force. Along with this direction of the fluid, you are going to have shear stress distribution. It means that what happens is going to have friction because of the viscous effect on this surface, and then because of that there will be a shear stress, and that stress will cause a drag force, and that drag force will be normally this direction. So our object is moving in this direction, drag will be in opposite direction altogether. So that's my drag force. So if object is moving in that direction, drag will be in this direction, and this one is a drag force. So what we learn is a lift force is perpendicular to the direction of the fluid, and it is in this case it is upward direction. Drag force is a parallel to the direction of the fluid. In this case it's opposite of the direction of the, it's horizontal of course, but opposite of the direction of the object, and all together combined I can call it as lift force, and drag all together combined I can write it like this here. So here lift force acting upward direction, drag force acting upward direction, and these are the two forces that act on the body. So collectively you can imagine, so this one is depending on the intensity, probably the resultant force will be somewhere in this direction. So that's what happens whenever you have any object, your car is moving, your car has these forces acted on it, some lift force, some drag force, and then all together there will be some resultant force, and these are the forces that we'll try to understand in this chapter. So how to calculate these forces? There are two ways to calculate these forces. One is relatively conventional method, and then another is direct method with formula which we use, but we will see both of these methods. So first one, lift force or lift and drag concepts, and the conventional method here. So let's say I have a car and then it's moving in this direction, in X direction, and I want to know lift force and drag force on this car. So now what I do is that we try to understand, we take a very small element of the car, let's say the element here at windshield. I'm going to take a very small element of the car, I'm going to try to understand my forces in X direction and Y direction on that element, and then I'm going to integrate it for entire surface or entire body. That's the conventional method. So we take very small element, let's say I'm going to take this small element of this windshield here, and then I'm going to try to understand the forces on that. So this is the element here I'm going to take here. So this is the element that I'm going to work with. That's a small element, windshield element here. And then this is at an angle theta. So whatever the angle is making, it's a theta. And I want to know lift force and drag force. So here, first thing first, I'm going to try to understand all the forces in X direction on that element, and on the forces in Y direction on that element. It's a very small element. So here all the forces, so here basically there are two forces acting on the body or on the element. One is a shear force. Shear force is given by tau dA. Now I don't know if you can see it here, but I can write it down here. Tau dA. Now dA is the area of that element. dA because this is a small element, so I'm going to that small area of the element, and tau is my shear force, which is acting parallel to the surface. And then there is a perpendicular to the surface, which is your pressure force. That will be my P into dA. That's my pressure force perpendicular to the surface, tau dA and P dA. These are the forces acting on that element, and I'm going to put that here. And now all the forces in X direction and Y direction. So if it is in X direction, this force will be resolved in X direction here. So this is Y direction, X direction, and same thing for this force here and here. So that's what I'm going to do here. And then we are trying to understand these forces, tau dA and P dA. So here all the forces in X direction, now element is small, so dFx is equal to P dA cos theta plus tau dA sin theta. These are the forces in X direction. Now if we resolve all the forces in x direction here, for these two I will get P dA cos theta and tau dA sin theta. All the forces in y direction is minus P dA sin theta, minus sign, because if this force is acting downwards, if it is in y direction, this is acting in downward. So that's my minus sign there. So minus P dA sin theta plus tau dA cos theta, these are the forces in x and y direction. Now if I want to know entire surface or entire body, I am going to simply integrate it. So integration here dfx and dfy. This is my drag force, this is my lift force, and then I can calculate it. All I have to do is do this integration or put the numbers in whatever it is, and then solve this problem for lift force and drag force. The problem is that all the bodies are not same. So it is very difficult to do this integration. You can do that, you can calculate lift force and drag force, but it's relatively difficult to do that. So there is another method to do that beyond this one. There is another method which is a direct method with which we can understand this drag force and lift force by using a simple formula. Now in the past there are many scientists, many mathematicians, they worked to understand this, and then with that we have come with a simple formula. This formula involves something known as lift coefficient and drag coefficient. So it is a coefficient, it is unitless, it does not have a dimension, and we simply get the number, let's say 0.5 or 0.7 for these coefficient, and then you can solve the problem. So for that we have this kind of formula. For lift coefficient we have CL is equal to lift force divided by 1/2 density velocity square area. So whatever your object is, you have your velocity here, we have some surface area here, and then if I want to know lift force on this object, I need to know coefficient of lift, or if I know lift force, I can calculate coefficient of lift. Same thing with coefficient of drag. We have any object here and we want to know drag force. All we need to know is coefficient of drag, and once you know that, you should be able to calculate drag force, or vice versa. Drag force knows, you can calculate coefficient of drag. So, and here surface area of the object, velocity of the fluid, all together we can put that in the equation and you can solve this problem. So in simple words, if you want to know drag force and lift force, all you need to do is use these formulas and calculate lift force and drag force. So let's do a problem. They are quick simple problems to understand how this lift force and drag force work. So here I have a plate, a flat plate, 1.5 meter by 1.5 meter. This is 1.5, 1.5. It's in stationary. It's moving in stationary air. So this entire plate is moving with 50 km per hour. You have to convert that into meter per second, and then you have to find out what is the coefficient of drag, what is coefficient of lift, what is resultant force, and power required to keep the plate in motion. So you need to know lift force, you need to know drag force, you need to know resultant force, and then you have to calculate power required. Power is force into velocity. So whatever your horizontal force, which is the drag force, into velocity, that will be power required in watts. So here, first, it's very simple problem. All you have to do is put the numbers in the formula to calculate lift force and drag force. So what they have given is coefficient of lift and drag is given. So coefficient of lift, CD is given 0.15, CL coefficient, the coefficient of drag is 1.5, coefficient of lift is 0.75 is given. All you have to do is use these numbers into this formula and then calculate your lift force and drag force. It's very easy. Once you have lift force and drag force, you have lift force, drag force, you can calculate resultant force by using Pythagoras. It means that resultant force will be a combination of these forces. And then the power required is easy. Horizontal force multiplied by your velocity, F into V, and that will be power. Power is nothing but force into velocity. So now all you have to do is put the numbers in the formula, and if you do that, lift force, you have to calculate. I'm going to arrange the formula, and then I do that. I'll get coefficient of lift is around 100, and I get lift force is around 187.2 Newton, and then I'll get 37.4 Newton as a drag force. That's pretty much it. All you have to do is punch in the numbers. Now you have lift force, now you have drag force. Resultant force is Pythagoras, 187 square plus 37 square under root, whatever the answer, that will be your resultant force. So here resultant force is simply Fr, is equal to under root FD square plus FL square, and then in this case it comes around 190.8 Newton. So that will be in this direction. And finally, power required is horizontal force into velocity. So horizontal force is a drag force into velocity. That's the power required. You need to keep it in motion altogether, and that will be around 520 watts. So that's the power you are going to need to keep it in the motion, and that's pretty much it. So 37 into whatever the velocity you got, you put that there, and then 527. So here you have to convert that into meter per second. Keep that in mind. Then you can do this simple calculation. There is another simple problem, exactly like same, but in this case, our plate is fixed and then it's in wind tunnel. So experiments are conducted in wind tunnel with wind speed. So this plate is in wind tunnel, and then the velocity of the air is in 50 km per hour, and then the size of that plate is 2 into 1, so 2 meter by 1 meter, that's the plate. And we want to know what is lift force, what is drag force, what is resultant force, what is resultant. In this case, we want to know what is the direction of the resultant. What is direction? Direction is angle theta. So we want to know what is theta here. So we have lift force, we have drag force, we have resultant force. We want to know theta, and that's the answer. So we had to find out the angle. So resultant force, lift force, drag force, and then the direction is theta, and then power exerted by air on the plate, which is horizontal force into velocity Fd into v. So we can calculate that, and we should be able to get that. So here it's simple. The formulas are given. All you have to do is punch in the numbers in the formula, and you should be able to get that. It's very easy. So here, if you can pause and you can do your calculations if you want. So some calculations are here. So here I have lift force is equal to, this is the formula I'll get. The velocity conversion 13.8, this is 50 km per hour. You need to convert that into meter per second, so that will be your 30.89, 166 Newton. So that's your lift force. Drag force you will get around 33.28 Newton. All you have to do is punch in the numbers, and then resultant force is 169 Newton. So this one is a resultant. You are going to get it around 169 Newton. Once you have that, the direction of the resultant force is very easy. Direction is tan theta is equal to FL by FD. So all you have to do is simple trigonometry, and you should be able to calculate that. So tan theta is FL by FD. Tan theta is equal to phi, and then theta is equal to tan inverse phi, around 78 degrees. So this theta is 78.6 degrees. So that's the direction of the resultant force. And finally, power exerted by the air on the plate is nothing but drag force into velocity. So whatever your velocity is, 13.89, that's your velocity. Drag force is 33. You use that, and then you should be able to get power required here. So 462.2 watts, that's the power you get, and that's the final answer. It's very easy. If you know formulas, you can calculate lift force and drag force. Let's do another problem. Now in this problem we have a truck, and it has an area of 6.5 meters square. So whatever the frontal area we have here is 6, or whatever the area we have is 6.5 square meters. It's moving around 70 km per hour. So 70 km per hour, you have to convert that into meter per second. And total resistance is 2000 Newton. So whatever the resistance here, altogether, resistance means opposite of the motion. So motion is in this side, resistance will be in this side. So total resistance is equal to 2000 Newton. That's your total resistance. But out of that 2000 Newton, it says that 20% is rolling friction, 10% is surface friction. So rolling friction is friction in the tires, and another part of surface friction, and that's together is 30%. So 20 and 30. So it means what it says is that the rest is due to drag. It means out of 2000 Newton, 30% is this, the rest 70% is a drag. So we need, whatever the drag force will be 70% of 2000 Newton. So we have to multiply it by 0.7, and if you do that, you will get your drag force to calculate that. So here resistance is 2000, and drag force, that will be my FD, will be 2000 into 0.7. We have to calculate the coefficient of drag. The density of air is given. So all we have to do is find out this CD, and that's pretty much it. So calculate FD. FD is very simple. 2000 into 0.7 is around 1400 Newton. So you get that 1400 Newton here, and then velocity you have to convert it 70 km per hour into meter per second. So whatever that conversion is. Area is given 6.5, and here density is given 1.25. So all you have to do is punch in the numbers and calculate that coefficient of drag. So here, if you calculate that coefficient of drag, first you convert your speed of truck into meter per second, which is 19.44 meter per second, and then your drag force is 1400 Newton. So now you have drag force, you have your speed in meter per second. All you have to do is put the numbers in, and then you will get coefficient of drag around 0.912. So that's the answer you will get. Now 0.9 is a quite high drag. You want your vehicle is more efficient. Normally for truck 0.4 or 0.45 or 0.5 maximum should be efficient truck. More than that, you are going to lose a whole lot of fuel, extra fuel, unnecessary. So high drag coefficient means high drag, it means you're going to lose more fuel. So you want to be more aerodynamic in that sense. So in the past, in 1920s and 30s, when there were car coming for the first time for some 100 years ago, there were these box shaped cars, and the reason is that the priority at that time was to make this car running and then without breaking down somewhere in the middle. So they didn't really worry at that time about aerodynamics. Apart from that, the velocity of these cars wasn't very high. So aerodynamics wasn't really much of a point. But later, as our understanding improved, the shape of the car changed. So now in 1940s and 50s and 60s, you have this kind of car. So initially you start with very high drag coefficient, which is 0.8 or 0.9, and then later the drag coefficient, average drag coefficient decrease, which is around 0.6 or 0.7, and then by time 80s and 90s, you have this kind of car where we have drag coefficient around 0.3 or 0.5, 0.3 to 0.5, and then later now we have very fast cars, something like this, sometime early this century, and then they have drag coefficient around 0.2, maybe less. So if you have that much amount of drag coefficient, it means less drag. It means that your vehicle is more fuel efficient. More drag, more the fuel, less drag, less fuel. So here, now here. So that's, you can see the graph total is coming down, and then that's how our understanding about this drag force and lift force increased with time. Let's do another problem. Here in this problem we have a man weighing 90 kilograms. So there is a man, let's say there is a man here, and he is 90 kilogram, and then he's gonna 90 kilogram descends on the ground from the airplane with the parachute. So he's gonna jump with the parachute, and against the resistance of air, the velocity with which he's going to come down is 20 meter per second. So he's coming down with 20 meter per second, and then we want to find out what is the diameter of the plane. So altogether I want to know what is this diameter for this velocity and this weight of the man. I want to know that, and then here the coefficient of drag is given 0.5 meters. 0.5, so drag coefficient is 0.5, and density of air is given 1.25 kilogram per meter cube. So now my objective is to calculate diameter. If I know area of the parachute, I should be able to calculate the diameter. So that's the idea, to calculate area. So here I'm going to put my numbers in. Drag force is downward force, which is weight of the guy. So 90 into 9.81, 90 into mg, 9.8, that will be my weight. 90 kilogram into 9.8 newton, so that will be weight. So that's my weight is equal to mg, and then that will be my force in newton altogether, and that will come around 882.9 newton. And then 0.5 drag coefficient, we have to calculate diameter, so I'm going to put that here, pi by 4 d square, that's area, and the rest of the calculation you do that, you'll get around 3 meters. So that's the diameter you will get. It means that if by putting simply the numbers in, you should be able to get the diameter for this parachute, which is around 3 meters. It's again very simple problem. All you have to do is to punch in your numbers and calculate the diameter. Then the next part here, it's characteristics of flow past an object. So we want to know more about this lift and drag concepts. We want to know how do they exactly work. So what we do is we take some objects, let's say a plate, and then we put it in wind tunnel and we try to test it. So here I'm going to put this object into wind tunnel, let's say a plate, and then I'm going to test it at different velocities. So a simple plate, I will put it, and now at a very low velocity, and then I'll test it at very high velocity. So first, very low velocity, we have low velocity means laminar flow. So very low velocity laminar flow. Initially, you see the velocity pattern is exactly same, and then what happens is that we get some deflection here, and then flow deflects like this here. So we'll get some deflection, and then you'll get this kind of wake here, or this kind of pattern where viscous effects are important, and then as it leaves, you will see this kind of velocity profile. So initially everything is straight, and now you have different velocity profile. Here we have very low velocity, here we have very high, normal higher velocity, and then you'll get increase in velocity. That's what happened with very low velocities of the air. Now let's increase the velocity, let's increase the Reynolds number. And if you do that, what happens is everything is same, the dimension is same. What happens is deflection becomes much later. Now this is much closer to the body. So initially you got it here, now you are getting it here, and then the wake that you are getting, so this gray wake that you are getting here is much smaller. So here we have very large wake, here we have relatively smaller wake, and then the pattern when it leaves, it will say different. So here we have thick wake here, or thickness is higher, and then here we have lower thickness in this case. Then let's increase the velocity further, and if you do that, you will get this kind of wake. So here what happens is that the deflection you will get almost at the plate, and then you will get this kind of a boundary layer, very small boundary layer. Now this is very high velocity, Reynolds number is very high here, and then you are going to get the final very smallest thickness here in this case. So that's what you get if you test this object in wind tunnel. Let's change the object. Let's, instead of plate, let's keep a disc or a ball, a smooth sphere. If I put that, and then if the velocity is very low inside wind tunnel, you'll get this kind of very nice streamline, very smooth streamline, laminar flow. You'll get something like this. That's the flow you will get when the velocity is very low. Then if you increase the velocity, if you increase the Reynolds number, you will get this kind of region, or this kind of wake. So here you are going to get some deflection, but velocity is high, so it's going to jump, and it's going to come here, then it's going to come here, and then here you are going to get some separation bubble here. That's what you see at slightly higher velocity. Let's increase the velocity further. Let's increase the, if you increase that velocity, it's going to come here, it's going to deflect, and at very high velocity it's going to just continue to travel. And then here you have some air already, you are going to get some turbulence here, and that's your separated region. So your flow will separate somewhere here, and then it's going to go continue like this. And then the region, the air which we already have here, is going to start to get some turbulence here, and then that will create more drag. And that's your separate. So wherever that will separate, that will determine how much drag you're going to have. And that's what happens if you test this object in wind tunnel at very low speed, at normal speed, and then at very high speed. Now this part, what you see here, is known as boundary layer, and boundary layer is the result of of the viscosity or no slip condition. So what happens is that, as we learn for the viscosity, whenever you have whenever you have fluid flowing over object, you are going to have, because of the friction, zero velocity here, and then velocity will slightly increase, and you will get this kind of velocity profile. And then velocity comes around 99% of overall stream velocity. That's where you mark a point, and then you say that that's your thickness of boundary layer. Now that thickness is depend on viscosity of the fluid, total velocity of the fluid, overall surface friction. So all these factors will depend on this delta, and if you want to design an efficient machine or efficient aerodynamic design, you want to know how much this delta is, how much this boundary layer thickness is, and that's your boundary layer, one of your boundary layer characteristics. So let's say we have another plate, and then we are testing that plate in the wind tunnel, and then how does it look if we do it more close? if we take a closer look. So here in this case we have two particles, one particle here above the streamline. Now initially the velocity here altogether is same before plate, and this particle you can see here, this particle here, here, without interruption this particle flows, because this particle is much above the boundary layer thickness or overall boundary layer. So we are not worried about this particle. Now this is the particle which is much closer to the boundary layer or much closer to the surface, and which will be in the boundary layer. Now it goes here, initially it's same, and then you will see this boundary layer here increasing here, and then what we see, what we observe if we are doing this experiment, for some length we get laminar boundary layer. Laminar boundary layer means that our object will not change its path. So here my particle here, it is distorted, but the path is not changed, it is still in straight line. That's my laminar boundary layer. It means still it is normal one. And then later, after a certain period of time or after a certain period of length, what happens is that the path is changed, and that's your turbulent boundary layer. So here you have laminar fluid separation, and then you get turbulent boundary layer, and then now you have different path for the particle. It means that now your flow has become completely turbulent. So that's what you see. You will get first laminar boundary layer, and then you will get later turbulent boundary layer. And then here is one of the animation we have. Initially we have laminar boundary layer here, and then later it becomes more turbulence as we go ahead. And that's one of the characteristics of this boundary layer. Here we get laminar and then turbulence again. So this boundary layer concept gives rise to very important phenomena in physics, which is known as the Magnus effect. Now in 1852 there was this guy Henry Magnus, and then he understood this effect, and then because of that we can manage to curve the ball in air, whether it is table tennis ball or tennis ball, whether it is soccer, whether it is a baseball, any sphere you can manage to curve it through the air. Now how do we do that, and how this boundary layer works? So what happens, let's say the object is just moving. Let's say you have a smooth sphere, a ball, a soccer ball, any ball. It is just there, and then it is going through air. So in this case the object is moving through this, and then the velocity, the fluid is flowing over this, like this here. So here it goes like this, and like this, and then like this. So that fluid is normal. This object is not rotating at the moment. So that's what the pattern you will get, and then here you will get this stagnation point here and here. That's your pressure point, which is equal, which is at the center. Now let's assume that this ball is not moving but just rotating on its own axis. So here if we start rotating on axis, because of the boundary layer, because of the no slip condition, the air here will also rotate at the air molecules, let's say, or fluid molecules here will rotate at the same speed. So they are going to rotate. The molecule next to it will be rotated with slightly higher speed, then higher speed, then lower speed, so slightly lower speed, lower, and then it will become normalized eventually. So that's the pattern you get when it starts rotating. So higher the velocity, the initial velocity will be higher, and larger the pattern. That's your rotational velocity. Now let's assume that we have combination. We have combination of the object moving in straight line, at the same time it's rotating. So if you do that, if you put the object in straight line and at the same time rotating, what happens is now you will get change in pattern. So it is rotating at the same time it's moving, and therefore this stagnation point, this point shifts. So this pressure point shifts. Now in this case the object is rotating clockwise direction and then moving in this direction, and then air is moving in that direction. So here, because of its moving there, and your stagnation point shifts lower to the surface, and then it's going to create upward force. So what happens is that you will create a lower pressure here, high pressure here, and because of that it's going to move and it's going to curve, it's going to get this upward motion, and that's the general idea of Magnus effect. I'm going to put some videos in your black PowerPoint to understand in detail, and then once you understand these videos, you'll understand more about Magnus effect. So make sure that you learn these videos. It's very simple. All you have to do is combination of two things. It's moving in straight line, at the same time it's rotating, and if you can do that, if you can give that spin, you manage to curve the ball, and that's basic physics of these objects. Then final part is golf ball or table tennis ball. So here we have a golf ball. In the past, when 200 years ago, when they started playing golf, they did have this very smooth balls. What happens is that if you use smooth golf ball, you'll get your flow separation here. If you hit the ball and then it's moving in that direction, the airflow is in this direction, so you will get your flow separation here, and then flow is going to separate and you're going to get very thick wake. And thicker the wake, you're going to have more drag. So here you are going to make more drag force, and then this ball will travel less distance. But nowadays what we do is we put some pimples on it, or here we have this small dots on it, and then if you do that, if you have some pimples here on the ball, what happens is that this separation comes very late somewhere here. So instead of separation getting here, you're going to get it here much later of the ball. And then you will still get some wake, some drag force, but it will be much lesser than this one. So here now you will get very thin wake. It means that you have lower drag here, and this ball will go much faster. So in this case, this ball, the weight is same. The force you are going to push them is exactly same. But because of the dimples, you are going to get higher velocity, and it is going to cover a higher distance. This one is going to cover less distance. So that's the reason that we have dimples on these golf ball. And again, I'm going to put a video for the golf ball, and then you will learn more about this boundary layer separation. Then final part, lift and drag coefficient on a smooth spinning sphere. So you have a smooth sphere, let's say table tennis ball like this one, and then you are rotating it at very high speed, and then it's also moving in some direction. How to calculate lift force and drag force on this smooth sphere? To do that, use this kind of graph. So to calculate this drag coefficient and lift coefficient, you need to know omega, which is the speed, diameter of the ball, and to velocity, what velocity, what horizontal velocity it's moving. So this ball is moving with some horizontal velocity, so fluid velocity is in this direction, it will move in this direction, it's rotating clockwise, and then lift coefficient and drag coefficient is given by this formula. So here, if I calculate that omega d by 2u is equal to 2, then I'm going to draw my vertical from that 2, I'm going to mark a point, and then I'm going to draw a horizontal, and then that will be my drag coefficient. So that will be my lift coefficient. Sorry, this one is lift coefficient. So lift coefficient in this case will come around 0.36, 0.37, something like that. And then I'll continue my line. My drag coefficient will be somewhere here, and then that will be 0.6. So that's how I can calculate. If I know lift or drag coefficient, I can calculate omega. So if it is 0.2, then in that case lift coefficient will be somewhere here, and then once I know lift coefficient 0.9, I should be able to calculate omega d by 2u, from which I can calculate its rotational velocity, and that's how we can calculate lift and drag coefficient for smooth sphere. So let's do a problem. This is the last problem, and then we can stop for this chapter. So what happens, what in this problem we have is a table tennis ball. So we have this table tennis ball, which is a smooth sphere, and then weight of that ball is given. So weight of that is 0.0245. So the weight here on this ball is acting as 0.024 Newton, 245 Newton. So that's the weight acting downward direction. Velocity, the diameter is 0.38, so diameter is 3.8 centimeter is given. You have to convert that into meter, that's will be 0.038 meter. And then velocity is 12 meter per second. So you're going to hit it, and then it's going to go in this direction known by 12 meter per second. So that's it's given. What should be the value of omega if ball is to travel with horizontal path without dropping due to acceleration of gravity? Now, what's going to happen is as soon as you hit this ball with 12 meter velocity, gravity is acting always downward. So it's going to, if there is no spin, then it's going to follow this path because of the gravity is going to come down. But if somehow you can manage to spin it in anti-clockwise direction, in this case, then it's going to generate a lift. And because of that, instead of going downwards, it's going to follow exactly straight direction without going down, and then that you could win a point because of that if you're playing table tennis. So you have to give the spin. In this case, you have to calculate what value should be that spin, what value of omega, what is the RPM value or radian per second value, what is the value of omega, what should be the spin in order to get this path moving. So in order to do that, this spin should be enough, it should generate a lift force in upward direction which is equal to weight. So here 0.245 Newton downward direction, we have to balance that gravitational force. So my lift force FL should be, to balance that, 0.0245 Newton, and that's the idea. So if I can somehow balance this force downward direction, I should be able to calculate with the spin, this should go in horizontal direction. So that's the general idea for this problem. So for this problem, we are going to use this formula and this chart to calculate that omega, the spin for the ball. So here, first thing first, we need to calculate lift coefficient. Once we have lift coefficient, we are going to use this chart. So in this case, let's say we get your lift coefficient, this one is lift coefficient. Let's say lift coefficient is around 3. In that case, at this point 3, I'm going to mark horizontal, vertical, and then lift coefficient we get around this point somewhere here, and then from this point, let's say, go back again. Okay. So here, let's say I get around 3.6. Let's say our lift coefficient is 3.6. So I'm going to mark here, and then from that 3.6, I'm going to mark a horizontal, and wherever we'll meet that horizontal, I'm going to draw a vertical from there, and then I'm going to mark a point, and then I'm going to calculate omega. So that's the general idea for this problem. So here what we do is that first we calculate our coefficient of lift. We have lift force, which is weight of the ball. So I'm going to put that there, and then I'm going to calculate lift force as 0.244. Now all I have to do is locate that 0.244 here. So here is my 0.2, here is my 0.3, here will be my 0.25. So 0.244 will come somewhere here for the lift coefficient, and then for that I'm going to mark a point. If I do that, here I'll get some point here, and from that point I'm going to draw a vertical like this, and then here it will meet, and then that point will be my omega d by 2u, that's the value. So here I will get omega d by 2u is around 0.9. So if I do that, I'll get 0.9. Now all I have to do is use this, solve this one, 0.9 omega d. I have diameter, I have velocity 12 meter per second, and then I can calculate omega. So if I do that, I'll get my omega 568 radian per second. So that's the omega you will get in radian per second. Now you have to convert that into RPS and then RPM. To do that, you have to divide it by 2 pi. 2 pi is 1 revolution. So 568 by 2 pi you will get in revolution per second, and then multiply by 60, you will get RPM. And if you do that, divide it by 2 pi, multiply it by 60, you will get around 5424 RPM. That's the speed that you are looking for. It means if you are playing tennis ball, if you can manage this thing to rotate at this velocity 5400 RPM, then instead of going down, this ball will go in horizontal direction, and that's the problem, and that's the that's the answer that we are looking for, 5400 RPM. And that's your chapter 9. We'll stop here today. These are some practice problems for you to solve. They're going to have an exam first week of November on chapter 8 and chapter 9. That will be our second exam, and we are going to have review class before that. If you attend the class, you will know that I'm not going to post video for the review class, but that's our chapter 9. Well, that's a good time to stop. I'll stop here now, and stay safe and stay healthy.